Hi everyone. So in this video we'll talk a bit about connectedness, which is something we actually have defined before and which we used in the characterization of Eulerian graphs. I'm just going to formalize the definition once again, give you the actual definition, define connected components of a graph, and then give you an idea on how to solve an example. So connected graphs, once again, these just mean between any two vertices in your graph, no matter which two vertices you pick, you will always be able to find a path connecting them or between them. Right? And so simply as the name suggests, right, connected. Like, what do you mean when you say a network is connected or you're connected to the internet? Right? There is a way for you to access that information. There's a way for you to get from point A to point B. So in this graph, for instance, which is called the Peterson graph, if I take this vertex as my vertex U and this vertex as the vertex V, then you can immediately see, yes, there is a path from U to V, traversing these other vertices in the middle. And for any two vertices in the graph, this is true. Therefore, this is connected. Right, so simple enough. You'll easily recognize when a graph is what we call disconnected. Say this graph here, consisting of two triangles or three cycles. This is disconnected because I can pick U here and V in the other triangle. And there's going to be, well, no way to get from U to V using a path in your graph. Now note that I could have picked U and V to be in the same triangle, and yes, there's a path in that triangle, but this condition has to hold for all choices of U and V. Okay, so if you can find a pair U and V such that there's no path between them, then that certifies that your graph is disconnected. Now, what we call the connected components of a graph is basically any maximal connected subgraph of G. Okay, so what do these words mean? You've seen subgraphs before. These are basically graphs that are contained in G. Right? So for instance, this triangle is a subgraph. Right? The triangle formed by vertex 1, 3, and 4. Assuming graph G is everything here, right? Just to make this clear. Now, that subgraph is connected, right? That triangle that is highlighted there. But it's not maximal in the sense that you can include or append more vertices, more edges into that triangle and still keep it connected. Right? So that's what the word maximal means. Can you add any more edges to your graph? If the answer is yes, then it's not maximal yet. And so the maximal connected component corresponding to this subgraph with 4 vertices is this entire thing. So I would say something like H, which is this graph, 1, 2, 3, 4, and all the edges that were there in G, is a connected component. Right? Now if I just take 1, 3, and 4, this is not a maximal connected subgraph. Well, I should say not a maximal connected subgraph. Okay, and so for the graph G here, there are 3 connected components. 1, 2, and 3. Okay, so to end this video here, I just want to talk briefly about this exercise, which actually, if you read it, it seems very obvious, right? And a lot of statements in graph theory are like that, where you probably think, well, if I have two graphs that are isomorphic, one is connected, clearly the other one has to be connected, right? There's just no other way. But how would you actually prove that? So I'm not going to write out the entire proof here, because I want you to try writing out a proper proof yourself. But I'll give you an idea of why it's true. I mean, again, clearly, you probably understand why it's true. G1 and G2 look the same as graphs, right, when you remove all the labels. But one way you could prove it is by using the definition of an isomorphism. But remember what an isomorphism is. It's a function, f, that is bijective between the two vertex sets. Furthermore, f preserves adjacencies. Preserves adjacencies. Right, and again, what that means for us is if the edge uv is in the edge set of G1, then f of u and f of v are in the edge set of G2. And the implication works both ways, right? It's an equivalence. And so, just to get you to practice, right? How do you prove a graph is connected? So again, go back to our definition. You just have to show that for any two vertices you pick, you can always find a path. So we're showing that G2 is connected, not G1. We know G1 is connected. So you want to show that if you pick two vertices in G2, then you want to show that there is a UV path in G2, right? Or a path from U to V. And that's the idea of the proof here. And what you're going to do is, or what you have to do, is go back to G1 and use the fact that G1 is connected. Right? The bijection helps you do that. U and V are in V2. F helps you get two corresponding vertices. F inverse of U, F inverse of V. Right, so I can just say our vertices of V1. Right, F is a bijection, so clearly they're distinct vertices in V1. And since G1 is connected, there is a path. I guess I'm proving it now, essentially. It's not a difficult proof. There's a path F inverse U to F inverse V. Right? Because there's a path between any two vertices in G1 because it's connected. Okay. So this is what I'll leave for you at the end. How does this translate over to a path in G2? Right, so your final sentence must look like, thus there is a UV path in G2. proving G2 is connected. All right, so fill in that last step there yourself. Using this path in G1 between the pre-images of U and V under that bijection F, can you use that to get a UV path in G2, which proves the result?